this lecture I will talk about what are called as special matrices, okay. And I have used the word special, but basically we will be looking at matrices that are symmetric orthogonal, and we will be looking at complex matrices and the corresponding and the complex matrix corresponding to symmetric and orthogonal real matrices. So, first let us consider a real, I will use the word square matrix A, and I will say n cross n. So, it has n rows and n columns. So, it is a square matrix. So, the number of rows and columns is the same. Okay. Now, if you consider a real square matrix, okay, and again we will use this notation that we are familiar with, A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN. Okay. Now, in this matrix, this set of elements, this is called the diagonal elements of the matrix. So, these are called the diagonal elements of the matrix. Okay. So, the elements along the diagonal are referred to as the diagonal elements of the matrix, and these are called the off diagonal elements. So, all the others are called the off diagonal elements. Okay. Now, suppose you had a real square matrix, an n cross n square matrix, okay, such that the A I j equal to A j I for all I and j. That means, or I can say A21 equal to A12, A31 equal to A13, and all the way, and then similarly A32 equal to A23, and so on. Okay. So, if you had this case, then A is said to be symmetric. Okay. So, A is said to be a symmetric matrix, okay, and it is very obvious what it will look like. So, what will it look like is that you will have A11, A22 up to ANN along the diagonals. Then whatever you have here, A12, the same A12 you will have here, A13, A13, and so on, A1n, A1n. Okay. So, these two elements will be same, these two elements will be same, and so on, and you can do for all the other elements too. Okay. So, an example of a symmetric matrix. Okay, I will just take a 3 by 3 matrix and show you what. So, suppose you have let us say 4, 5, 9, minus 1, 2, 2, 3, 3. Okay. So, this is clearly a symmetric matrix. Okay. So, a symmetric matrix is one kind of special matrix. Okay. Now, the next matrix that I want to talk about is what is called an orthogonal matrix. Okay. In order to describe an orthogonal matrix, okay, let me define. So, first define transpose of a matrix. So, A transpose is equal to, okay. So, A transpose is also a matrix. So, it is denoted by this way, and what you do is you basically swap the rows and columns. So, if A is given by this form, okay. So, if A is given by this expression, Okay. So, A transpose is also an n by n matrix, and what is done is A 1 1 and then you put A 2 1, A 3 1 up to A n 1, A 1 2, A 2 2 and A 1 3 all the way up to A 1 n here, and in this case A 2 1, A 2 2. Now, what you will have is A 2 3 all the way up to A 2 n, A 3 2, A 3 3 all the way up to A 3 n, A n 2. Okay. So, this is a transpose of A, okay, and you can clearly see what happened is you just swapped the off diagonal elements. You kept the diagonal elements the same and you swap the off diagonal elements. Okay. So, basically your transpose means switch rows and columns, swap rows with columns. Okay. So, the transpose of a diagonal matrix is defined in this way, okay, and what you can so we can clearly see that for a symmetric matrix, A transpose equal to A. Okay. For a symmetric matrix, A transpose is equal to A. Okay. Now, let us go to the next thing, which is a diagonal matrix, okay, and here or an orthogonal matrix. Okay. So, now let us get back to a matrix as a transformation of a vector. U, which is a vector. So, A u equal to V. Okay. So, it takes U, it transforms it, it is a linear transformation, it gives a vector V. So, if the norm of U equal to norm of V, okay, that is i.e. U and V have same magnitude. Okay, and we are talking about the usual norm. Okay, so if U is equal to U is given by U x, U y, U z, then norm of U is equal to square root of U x square plus U y square plus U z square. So, that is the usual way you take the length of a vector. So, if a matrix A transforms a vector such that it preserves its norm, and this is true for any vector. So, a matrix A is such that whichever vector it takes, it transforms it in such a way that it transforms it to a different vector which has the same norm as the original vector. Okay. Then A is called an orthogonal matrix. Okay. If it transforms a vector such that it gives another vector with the same magnitude, okay, then A is said to be an orthogonal matrix. Okay. Now, in order to see the so what does it do? So, suppose you had a vector, okay, and you transformed it to another vector that had the same magnitude. Okay. You could have a different vector, you could have another vector, let us say, that looked like this, okay, and this might be transformed to some vector that has the same magnitude, something else. Okay. So, such a transformation is referred to as an so the matrix corresponding to such a transformation is referred to as an orthogonal matrix. Okay. Now, orthogonal matrices, you can immediately see that what is an operation that would take a vector and transform it to another vector that has the same magnitude. You could have things like rotations, reflections. That means if it just takes each vector and rotates it by a certain angle, okay, then you will get another vector with the same magnitude. You could have reflections. Okay, so you could reflect each vector. You could have inversions. Okay, so you could take a vector and point it in the opposite direction, that would be an inversion of the vector. You could reflect it about a plane. So you could take each vector and reflect it about a plane, and so on. So these are examples of operations that preserve the length. Okay, so these are the kind of transformations that we will see. Okay. Now there is another property of this orthogonal matrix which we will see, and in order to see that property, we will define something called a inverse of a matrix. So okay. Now we can now in order to do this, we said that a matrix is an operation. Okay, so matrix. So if you had a matrix A operating on a vector, okay, you get some other vector V. Okay, now suppose B operating on V gives you back U. Okay, suppose you find some other oh, I should not have the arrow on this. Suppose you find some other matrix B which operates on V to give you back U. Okay, so then we can write as B operated on V, and instead of V I will write A U equal to U. Okay. And so now A and B are matrices, and you can show that that this is just this I can write as B A operating on U is equal to U. So B A is a product of two matrices. So this is the usual matrix product. Okay. And I expect you to know the usual matrix product. If you are not familiar with it, it's no problem, you can learn it very quickly. Okay. But if you take this product of two matrices and you operate on U, you get exactly U. Okay. Now what is a matrix? What is a matrix that operates on a vector to give you back the vector? So what can be a matrix? So suppose I take I will just take a 3-dimensional vector. Let me take Ux, Uy, Uz to give you the same vector Ux, Uy, Uz. Okay. So now what I should have here is you can easily show that if I take 1 0 0 0 1 0 0 0 1, okay, if I take this matrix, operate on this vector, I will get back this vector. So clearly, so this implies that I times U equal to U, where this matrix is called the I matrix, identity matrix. Okay. And now when you take the product of B and A, so this also implies that B times A equal to I identity matrix. Okay. So thus what you can say is that if B times A is the identity matrix, okay, so then B is called inverse of A okay. And and you can do this the other way also, B is called inverse of A and A times B is also equal to identity. So, A is inverse of B. So, in other words, A if B is inverse of A, then A is inverse of B. Okay. So, so this is the idea of inverse. So, in general notation is A inverse of A is denoted as A inverse. So, if you have a matrix A, then inverse of A is denoted as A inverse. Okay. So, now we can go ahead and we can look at this orthogonal matrix. Okay. So, the orthogonal matrix has a very special property for the inverse. So, if A is orthogonal, okay, then what we said is that A operator on U gives me V such that U and V have the same magnitude. Okay. So, now suppose so the norm of V I can write as in this form. So, I can write it as V transpose V. Okay. So, V transpose is given by this. So, V x, V y, V z. So, this is a transpose of a matrix that is not square. So, and V is V x, V y, V z. So, I can define the transpose even for a matrix that is not square. So, I had a 3 cross 1 vector, okay, its transpose will be a 1 cross 3 row vector. Okay. So, and if you take the usual matrix product, this is just V x square plus V y square plus V z square. Okay. So, norm of V square. So, this is norm of V square. Okay. So, now suppose I take V transpose V. Okay. Now, so that is A u the whole thing transpose A u. Okay. Now, A u transpose I can write as U transpose A transpose. Okay. So, whenever you take a transpose of a product, it is product of the transpose, but in the opposite direction. So, you have to switch the order, okay, and then you have A times U. Okay. So, if V transpose V is equal to U transpose U, and just put vector signs everywhere. So, if this V transpose V is equal to U transpose V U, okay, that is norm of V is equal to norm of U, okay, then we must have A transpose A should be equal to the identity matrix, okay, because if A transpose A was identity, then this will be identity times U, which is just U, and U transpose U. Okay. So, thus orthogonal matrix satisfies A transpose A equal to identity or A transpose equal to A inverse. Okay. So, this is what gives you what is called an orthogonal matrix. So, an orthogonal matrix, so you can just do the transpose of the matrix, you can calculate the inverse, okay, and you can check whether the matrix is orthogonal or not. Okay. So, this is when A is real. Okay. So, we have seen that if A transpose equal to A, then it is symmetric if A transpose equal to A inverse, then it is orthogonal. Okay. Now, suppose A is a complex matrix. So, if A is a complex matrix, so this is actually a complex space, okay, which you often find in quantum mechanics. It is called a Hilbert space. Okay. So, you can also define the matrices on this complex space. Okay. Then define what is called a Hermitian conjugate. So, which is given by a dagger. Okay. So, this is equal to, you take A, you take a complex conjugate of A, and then you take a transpose. So, you take each element of A and you replace it by their complex conjugate, okay, and then you take the transpose. This is called the Hermitian conjugate. So, if A dagger equal to A, okay, then matrix is called Hermitian, and if A dagger equal to A inverse, then it is called unitary. Okay. So, all you did is, instead of having A, so for a symmetric matrix we had A transpose equal to A. For a Hermitian matrix you have A Hermitian conjugate is equal to A. Okay. Similarly, for a orthogonal matrix you had A transpose equal to A inverse. For a unitary matrix you have A Hermitian conjugate equal to A inverse. Okay. So, this is the Hermitian and unitary are the equivalent of symmetric and orthogonal matrices for real matrices. So, is the generalization of symmetric and orthogonal to complex matrices, and this idea of unitary transformations or orthogonal transformations is again extremely useful in several areas of chemistry. Okay. So, I'll stop this discussion on special matrices. Okay. We will look more closely at rotational matrices in the next lecture.